Good morning, everybody. For those of you who haven't met me before, my name's Martin Gillman. I am Head of Development for the Water business here at Atlantic Pumps and one of the regular contributors to the training. I've got quite a long background, as you can probably see from the many greys in my head, with pumps and pumping, especially difficult on difficult applications. I spent 22 years in total working for progressive cavity pump manufacturers, CPEX and Roto. And I've worked in or delivered sort of solutions, I suppose you'd say, in many different industries. The bulk of my work has been in water and wastewater. However, I've also been involved in the oil and gas market, biogas, so AD, and food and beverage, and the various applications you might find in there. And today we're going to go through some training slides, and we're going to have a discussion about progressive cavity pumps, because this is part of the progressive cavity pump training series. We'll learn a little bit about the basics of how the pump operates, how it's constructed, because that's quite important to build up to the main part of this topic, rather, which is how we can test them in position, okay, without having to take them apart in any way. Okay, so what we're going to do is I'm going to share the screen, and hopefully everything will be all okay. So let's expand that to full screen, and we should be good to go. Right, so as I said, first we're going to start off, okay, with some ideas about the basic construction, because this is always a good foundation for this kind of training, you know, and a wash up or a brush up for those of you that may feel that you already understand these kind of pumps, these kind of machines. All right, they're pretty simple, really. They're just dumb iron and rubber, but we need to go through them so that we can get the basics in place. All right, then we'll talk a bit about some definitions, okay, some terminology, some wordings we use, especially in the PC or progressive cavity pump world, all right, which would make you sound really, really smart if you're not already, okay, and sharper when you're talking particularly to the manufacturers or consultants or whatever. It takes you upskills you that couple of steps, and also will help you identify and understand, you know, a little bit more about the nitty gritty when we get into it. Then we'll talk about some failures and faults that could go wrong and how we're going to fault find using the gauges. Okay, so should be quite straightforward. As you probably noticed, to reduce interference and accidental noises, we have the microphone switched off. But if you have questions, okay, you can either type them, and if I can immediately respond to them, I will, into the chat, that is. But if not, you'll see that my contact details are available, and you can always email me or call me at a later time. Always happy to attend sites if need be, providing it fits the calendar, okay, and actually, you know, consult on foot. More happy to do that if you've got some real troublesome applications or even potential applications in front of you. So without further ado, let's just quickly remind ourselves what a progressive cavity pump is. Okay, so if we consider the family tree, if you like, of pumps, it's over on the positive displacement side, not on the other side, which would be rotodynamic, like centrifugals and so on. Okay, and I like this first statement here. By the way, you'll get a PDF copy of all these slides, so you don't need to scribble down too much. Just sit back and enjoy. Okay, the PD pump is one which a definite volume of liquid is delivered for each cycle of pump operation. Now, each cycle could be one of several different cycles. In this particular case, it's one revolution of the rotor, okay, but if it's a piston pump or something like that, for example, it might be one stroke and so on. Okay, if it's a peristaltic, it might be one rotation of the rotor arm. You get the idea. But we're going to get what should be precise, or definite is the word here used here, volume of liquid moving forward. That will only change, okay, if there's a change in the system or to the condition of the pump. So if the pump is particularly worn, you might not get that full definite volume, because you may have some slip back, you may lose some, okay, so a little bit of volumetric efficiency is gone, okay, or of course if the system is in some way opposing it, i.e. the pressures are too high for the pump, or you're not getting fluid into the pump because its suction side, its delivery side is starved or obstructed in some way. But generally speaking, if all is well, for one rotation or one stroke, you get a precise volume of liquid, which is one of the reasons why they're very, very popular. Just one of them, of course, because we can get a nice, even, steady laminar flow, okay, out the pump with very little pulsation and a very precise volume going forward. So very, very small versions of progressive cavity pumps you'll often find. Walk past them, you might not even spot them. You know, the rotor and stators are the size of a large cigar sometimes, and they can be doing some quite detailed and accurate dosing okay, into other systems, because you can get them down to like a drip a second and so on, and be really quite accurate with it. Okay, and I've already talked about the progressive cavity is a rotary type. Okay, so it's on that side of the PD chart. Okay, and it's using a single helix rotor revolving, usually in a double helix profile stator, and that's how we get that sort of screw type pump. Sometimes they're called eccentric screw pumps. Okay, moving the liquid forward. The principle was quite simple, but you can make it far more complicated if you wish to. But as I've just touched on, essentially the rotor turns within the stator. The rotor is almost always, but not always, okay, of a metallic type construction. So it could be steel, stainless steel, it could be tool steel. Okay, it could be all sorts of things. There are some rare exceptions where they might be made of a ceramic or a plastic, but you won't really come across them very much. And that's a single helix profile you can see as you look at it. So it's basically just the spiral, the helix, okay? And the stator, is normally a steel can with an elastomeric or rubber type material molded into it, and that will be a double helix profile. So as the two go together, you get the cavities. Okay, so as the rotor turns, you can see the red there indicating the fluid moving through it. As the rotor screws, usually anti-clockwise, okay, but they can run both ways. Okay, you open up the first cavity, you create a slight, negative pressure. The liquid is pulled or flows in, and then it's conveyed or screwed or moved from one cavity to another, left to right in this case, out to the other end. So that's basically how the pumping action works. Okay, it's very good for generating higher pressures as well. Okay, and opposing higher heads, because the fit between that rotor and stator is an interference fit. It's quite tight. And so that sealing line, as we call it, we'll talk about that a bit more in a bit, okay, runs all the way through the full length axially of that rotor and stator. So you've got sort of a lot of contact between rotor and stator for any liquid or any pressure in the system to oppose. Okay, so that means it can push it forward with some strength, with some beans. So if we look at the basic construction and remind ourselves of that, okay, this is a typical single stage, what I would call single stage, meaning 6 bar and below, excuse me, progressive cavity pump. So if we start over on the left, we've got some kind of drive. Say we've got electric motor in this particular case, which would be the most common that you'll no doubt see. Between the main pump body, okay, the bare shaft as it's sometimes called, and the motor, you will have a reduction gearbox. Okay, very important for these pumps. It is rare, but you will find some very, very small pumps without that. They might be running on some kind of other synchronous or some kind of speed control straight directly into the motor. But usually we have a step down or a reduction gearbox between the motor drive and the pump itself. And that's there for two main reasons. Number one, the speeds at the shaft and the rotor on a progressive cavity pump are normally substantially lower than standard output speeds of whichever pole motor you've got. Okay, so we have that gearbox, of course, to step down that speed, but also the gear, and we're not going to get too deep into engineering right now, but the gearbox itself will also help you generate a little bit more torque and a bit more twist. And because that clamp, that squeaks, that tight fit I mentioned earlier on between rotor and stator, that gives you a certain amount of torque you've got to overcome just to get the pump turning. Okay, get it started, and we call that startup torque and then running torque. Okay, so you need that little bit of extra twist, okay, a little bit of extra beans to get the pump going, so that helps there too. Excuse me, the frog's in the chest today. But looking at the basic construction of the pump itself, we continue from the left. We've got, in this particular case, this is a heavy duty type pump, one of our own. So we've got a set of bearings integral into the pump body. That isn't always the case. I would say probably the majority of single and two stage pumps out there, so that means 6 to 12 bar, okay, in operation, will not have a set of bearings there. They simply rely on the bearing, which is already built into the front end of the gearbox there to hold this first part of the shafting concentric. Okay, it works to a fashion, but if you get any significant forces, especially axially pushing back through the pump, if there's higher pressures, then that can all that back on that single small bearing, and you will often get gearbox failures like that. So on heavier duty type pumps or standard pumps that are applied to much heavier duties, you will often see an integral bearing set as well. From the bearings, still with the input shaft we're talking about there, we've got some kind of sealing mechanism. Okay, in this particular case, it's a cartridge mechanical seal. And then the stub shaft or input shaft continues, and we've got our first universal joint. In fact, we've got two, and we've got what we call a coupling rod or connection rod shaft in between the two. We'll go back to that in just a moment. Let's just leapfrog forward to the rotor and stator. I've touched on that. You understand, hopefully, at least basically how that works. So this rotor will turn within the stator. There's an interference fit or clamp between that rotor and stator. Okay, one hard element and one slightly softer element, so we can apply that squeeze between the two, and it collects the liquid in the first cavity. In this particular case, it would be here, and it conveys it, helically all the way through the pump and out the other end. Now, because we have this helix into a single helix into a double helix configuration at the front, we therefore get some eccentric movement. So effectively, this end of the rotor, in fact, most of the rotor, but more so this end, will move up and down. Okay, that's just the way the pump works, the way that the mechanical elements have to operate. So because we've got eccentric movement here, and our input shafts and input shaft up to through the seal are concentric, we have to allow for that. So we've got this connection rod with two universal joints, one at either end, and that allows for the movement we need. Okay, and we're not bending and snapping shafts and things like that. There are other variants out there which have what we call a flexible shaft. The pumps are much longer, but they'll have a long, almost whip type shaft between this point and the front of the rotor, and it literally relies on that shaft bending and flexing in order to take up the eccentric movement. But we don't come across them as much as we do standard pumps with the joints. The rest, of course, are pump body parts. You can see that there's the inlet flange there. In this case, the pump body, or suction casing as it's sometimes called. And then you've got a small piece at the front end here, which is this pressure branch or discharge branch with the flange or the connection point there too. So let's remember mainly about the rotor and stator end, because that's the business end, that's the wet end, that's where we are going to find most wear and tear or damage is going to happen. Okay, and that's what we're going to be looking for later when we go through the testing. I'm not going to go through too deep into this because this is a generic set of slides, okay? But if we were going really deep into how these pumps work and the variations of them, I could talk about different geometries, okay? So you got basically, very quickly I'll do this. So you got conventional, which you can see has a very short pitch between the peaks or the points, if you like, on the rotor. Then you got very common version called L or long geometry, where it pretty much looks like the rotor and stator have been stretched. Okay, gives you a larger cavity, which means you can get a little bit more flow out per revolution. Okay, but it has got some downsides. It's a little bit more or less resistant to higher pressures and higher concentrations of abrasives because it's got less contact points. You could even see that as you glance. And then again, even more unusually, you've got something called trilobe or tricam, okay, which is a double helix rotor and a tri-helix stator, which we're not going to get into right now, but it works in the same way, same principle. You get a little bit less eccentric movement, but other than that, its main benefit is, again, you can get a little bit more volume per revolution. Okay, but the most common you'll find in most industries would be L or long geometry, okay, closely followed by conventional. A quick reminder about rotor and stator and how it applies to length. You notice what I mentioned earlier on when I touched on the sealing line, which is the connection or the touch point, if you like, between the rotor and the stator. You can see at each of these peaks between the pitch, okay, you've got, in this particular case, 1, 2, 3, 4, 5, 6, 7, 8, okay, roughly and a half perhaps. Okay, whereas the single stage, so the 6-bar pump rotor below, you've got half that. Okay, so it's pretty straightforward. We call a single stage usually up to 6-bar. Most manufacturers follow that rule of thumb. There are 1 or 2 that do 5-bar on a single stage, but again, they're rare, so we won't worry about that, but just for your information. Okay, call that single stage, and then up to 12-bar 2-stage, and then we would have 3-stage, which would be 18, so it's going up in 6s, you can see that, and then 24 and so on. Okay, we call that 4-stage. The way to get at least a feeling about what pressure stage or what pressure capabilities a PC pump might have at a glance, okay, is to look at the length of the rotor and stator. Okay, if it's got particularly long rotor and stator and it's quite narrow, it's probably a higher pressure version, okay, of a PC pump. So it just gives you that little bit of background understanding. All right, if you do approach one and you're unsure, just have that as a rule of thumb in your head. We talked about the universal joints. We're not going to go into these too deep because it's not the main topic for today's discussion. Okay, but that's the inside of a standard universal pin joint. Okay, if you ever want to refer back to that, as I said, you'll get copies. Okay, that's pretty much what it looks like. But in basic idea is you have a joint here, which is very much like, some people like the analogy of a CV joint on a vehicle, on a car. Okay, which is so you've got components there which are designed to move, and some sacrificial bushes in there. Okay, and it's shrouded in a rubber boot, which is held in place by these steel holding bands, and that will be lubricant filled, usually a grease, sometimes an oil. okay, so that you can allow for the flexing and the movement within that. They tend to fail either when they're overloaded, or you get a breach, a sort of rip or a tear in the rubber, and the fluid you're pumping gets in there, washes the lubrication out, and you get full lubrication failure. The other kind of universal joint you get on heavier duty pumps, pumps which are a little bit more, well, not designed, but a little more intended for higher pressures and harder work. Okay, you use full cardan joints. Okay, so I call them the knuckle and block, but that's just my name. So you've got the main center block there. You've got your two knuckles, and you've got two sets of pins. You might notice on the previous one, you've only got one main pin. So all your axial forces are applied, excuse me, across one area. Okay, but with a full cardan joint, you get two fully fitted pins, okay, going through there, so they're going to take a lot more loading. And this little separate image here is the same concept. It's still a cardan joint, but it's a much smaller one that you might find a much smaller pump. You can just see the connection rod there at the bottom right actually go how it would then push into the block here. The main pin would go through, and this little roll pin would secure the pin via the groove in place. But the principle is the same. These will also be shrouded in rubber to protect them. However, cardan joints are far more robust, and they can take a lot more work. And they tend to even continue to operate relatively well if they do get the rubber shroud ripped off, and so on and so forth, because they're sort of less vulnerable to lubrication failure. Eventually they will, of course, but they're less vulnerable. So you tend to find these on heavier duty pumps. Now for those definitions. Now we've done the background. Sealing line. The sealing lines I've already touched on. Okay, is the constant point of contact between rotor and stator from one end to the other. Okay, so I've marked the touch point with these yellow or orange, you might look on your screen, little blocks or markers. But don't forget, as I've explained earlier, the contact goes all the way along, okay, through in a spiral fashion or helical fashion all the way between rotor and stator. So that sealing line is actually a very long, continuous line, be it in a spiral shape, okay, form all the way through, okay. And it's that point of contact between the rotor and the stator which is essential, okay, for the pump performance, okay, for its efficiency. And then we got clamp. Okay, don't worry, I'll put all these keywords together in a moment for you. A clamp is very much related, but it's slightly different, and that is what we refer to the amount of interference, or I can sometimes call it the squeeze. I should have perhaps carried these arrows all the way through, but you get the idea. Okay, so you've got the continuous line, which is the sealing line, and that line requires a certain amount of clamp or squeeze or fit, tightness of fit all the way along it in order for the pump to operate efficiently. So we've got sealing line and we've got clamp. Okay, so far, and that's the two elements that we will see reduce or damaged or wear away or whatever, or be eroded as we get wear and tear on the pump and we lose efficiency. And finally, we got a term slip. Okay, familiar word to most of you, but how do we apply it into this kind of pump? So basically slip is the action, or the name we have for the action of some of the liquid that we're trying to pump forward actually being squeezed back between the rotor and stator. And as you can probably imagine in your mind's eye, that will happen more and more as the pump wears. As the clamp and the sealing line get reduced between rotor and stator, you'll get more slip. So it summarizes it here. Slip usually occurs due to wear and tear, okay, of the rotor and stator to the point where the pressure acting against the pump, so the discharge end, okay, begins to overcome the clamp. Okay, and then slip occurs along or at the sealing line. It doesn't always have to happen all the way through evenly. It might be a little bit more worn at the front end or at the back end or whatever the case may be, but slip is slip. So essentially, once we have slip occurring, we're now losing our volumetric efficiency. We're now losing our flow rate. So if our flow rate should be 10 meters cubed an hour and we've got significant slip, against our head of say 3 bar, we may now only be getting 7, 8, 6, whatever meters cubed an hour, because a certain percentage of it is actually slipping back through the pump and it's not all going where it should do. Okay, and the higher the head, the higher the discharge pressure, the higher the resistance to the pump, of course, the more slip's going to occur, because you've got more force acting and assisting that slip to occur. Okay, and of course, the same applies to the more wear you get, then the easier it's going to get. A really worn pump will begin to slip at perhaps only 20% of what its actual handling pressure could potentially be, because you just lost so much of that interference fit. Okay, so you don't need to write it down, but this would be one of the key phrases to remember from the training. Slip usually occurs due to wear of the rotor and stator. Sometimes it can be one or the other, but usually a little bit of both. Okay, where the pressure acting or the head acting against the pump overcomes the clamp. Okay. So that's really, really important. You kind of keep that in your mind, because that's going to apply directly to how we test a pump with gauges in a bit. So a few statements from me, and these next few slides I'm going to go through a little bit more quickly because they're not the main topic of this particular conversation. Okay, but never look at the pump as a standalone item. Okay, always view it as part of a system. Take a holistic approach to its failure. So when you do approach a pump and you are aware that it's not performing as it should do, it's not just the pump, and I'm doing the finger quotes. Okay, I don't like to do that, but it's not just the pump. Okay, as I said right at the head of this, it's just dumb iron and rubber. Okay, it will do its thing if everything around it is as it should be. Okay, apart from if it's damaged or worn, which we're going to be finding out about shortly. But effectively, even if it is damaged or worn, what caused it? What in the system is attributing to that? Because in a perfect scenario, like anything, like just like a mechanical seal, these things, they won't run forever, but they should give you a very, very good and long, comfortable service life. If they're failing every few months for some reason, maybe it's wear and tear or they're breaking somewhere, something else is at play. It always is, and it's up to us to find out what that underlying issue is. Otherwise, we're not actually fixing the problem, we're just fixing a symptom. Why do they fail? This is a little bit out of date, okay, but I'm not going to hang about on this one too much because it's out of date because gland packing is quite rare now, okay, on the input shaft of the pumps. Normally will be a mechanical seal these days, so that would slightly move, but the rest still does apply. Usually it's stator, being the softer of the two wearing parts, will be the most common part to wear first, closely followed by pin joints. The rotor actually comes after pin joints generally, okay, but not always. It really depends what you put through the thing. But generally speaking, that's what's going to happen. And if you really want a rule of thumb, and people often ask me this, but it is really rough because everything about using a pump and the system always should be preempted by the word "it depends," okay, what you're doing. But generally speaking, you should get 2 to 3 stators for every rotor. Okay, it's very common practice in most industries to change them both at the same time every time. That isn't always a need to do that. It costs a lot of money to do that and time. And with the right kind of training and understanding exactly what you're looking for to check if that rotor is actually properly worn or not, you might just change it. Okay, so again, contact us if you need to, if you want a second opinion, photos, or we can visit site. But so on a big pump, those rotors can cost as a spare part 3, 4, 5. I've seen them cost up to £20,000 on really big pumps. Okay, they don't always need to be changed. Get some training or an expert to give you an idea of whether it really does need replacing, because you could save an awful lot of money. So now we get to the nitty gritty of what we're here for today. We're 25 minutes in, so this is good timing. I'm going to take a little water sip because firing one's mouth off at this rate of knots is normally quite drying. So how can we health check a progressive cavity pump, okay, without disassembly? And it's really quite straightforward, actually. It's called a closed valve test. And as I go through it, I'm sure any of you with any technical understanding, and I don't know how many of you have or however you haven't, okay, a few pennies will drop and it will hopefully make quite some sense. But keep in mind what we have just learned about how the pump wears and what symptoms it gives us when it does so. Okay, which parts of the pump are actually going to be affected, because this will make more sense then. So the first thing that we need to do before we even walk into the plant room, perhaps, is get a copy of the data sheet. Now, the data sheet is kind of like a terrible analogy that I use. It's a bit like a birth certificate for your pump. Whenever you order a pump from an OEM or a reseller, okay, what you should get, and if you don't get this, put your foot down because it should exist, you should get a data sheet. You shouldn't just accept a pump on a pallet or in a box or in a crate or whatever and just assume it's going to be right for application, because somebody somewhere along the line could have made a mistake. Okay, they could have given some wrong information to the manufacturer or the provider, or the manufacturer or the seller could have made a mistake in the specification when they were preparing the pump. But every pump should be offered to you, applied correctly to the system in which you're going to use it. And what I mean by that is the pressures you're going to expect, worst case scenario usually, the flow rates that you want, okay, what the liquid is, its pH or pH range, its temperature, okay, its density, its dry solids content. All of this stuff needs to be known, okay, or should need to be known by your pump provider when you are requesting a pump from them. And what they do is they put all of this information into a configurator of some sort. Maybe some of them smarter, more old school ones might do it on a piece of paper or a whiteboard, but they will collate all of this, put it together, and it will then paint the picture of the pump that you need, okay? And that will be governed by all sorts of things. It will govern how fast you can run it, because the more abrasive the material that you're pumping, the slower you want to run that run that rotor in particular, because then you're reducing the rubbing velocities inside the pump, and therefore you were slowing down the wear, for example. Of course, they need to make sure the metallurgy and all the other materials in the pump, the rubbers, the O-rings, and that are compatible with what you're pumping. Okay, if it's indoor or outdoor, if it's got a gearbox, does it need a breather? If it's got a motor, does it need heaters and thermistors? All of these things, okay, should be considered up front to give you the best chance of getting the right pump to do the job, which you know is going to be reliable. And it should all be collated. And all those questions should even be asked by the pump supplier, because if they're not asking all of those questions, they're not doing a thorough enough job. So, hopefully we always do that. And I always have tried to do that. But, just be aware that you need that kind of technical element to support. If you're just getting a quote with one line on it and it says pump B, £5,000, how do you know you're getting the right thing? How do you know? You're just trusting somebody, which is okay if somebody's used many, many times before. But really, what we should be doing is our due diligence and getting the data sheet and just checking it. And what we would do is we get this data sheet in this case before we even walk to the pump, and we will have a little look at it and we will say, does this actually match the system that pump's in? Or has something changed over the years? Have we now got higher throughput? Have we now got, I don't know, more, the pipework's been extended, so the pressures might be higher? Or the opposite, lower? Or, have we changed it? Is it higher concentrations of dry solids than it used to be? All these questions need to be asked because they will be indicators to help you understand what the problem really is. We can't just walk up to a pump with a spanner or whatever and say, it's bust, mate, and start taking it apart. That's foolish. Okay, you're taking something out of service which might not be the problem. So we need to check the pressures, which would be on the data sheet. I know you can't read this, don't worry about it, but I'm just, the point is the point. Okay, so it's got the maximum pressure this pump should see in this particular case, and the pump will be right down to the actual pump serial number or model number. So it should be, as I said, bespoke to your actual pump. Pressures, flow rates that were required. So what you do is you do a quick cost check on that, because what you can do from here, you now have the benchmark, okay, what the pump should be doing. And if the system is not even wildly different than that, okay, if it is just different, then that gives you some early hints, some early understandings of what might the underlying issue be. Okay, for example, if it tells you that the speed, you can't see it, but I'll read it out to you. The pump speed in this case for the pump that we're talking about is 253 RPM. And that's how the pump manufacturer decided that's about the fastest speed you really want to be running it at for this particular application, which is a blended sludge in sewage treatment, okay, which will be probably got high concentration of grit in it and other debris that might not be welcome in the pump. So it's limited in its speed on purpose. Now, the WIMES industry specifications back this up and they give you guidance to do this. Okay, so it's not just something we make up. Okay, you should be watching those guidelines. We'll talk about them later. But the idea is that you need to check that's still the case, because if somebody has, let's say this pump is operated on a frequency inverter, on a drive control, and somebody has taken it beyond 50 hertz and it's now running at 350 RPM at the rotor, you're now running that pump far too fast for the abrasive content of that liquid. So no wonder it's wearing out quickly. And you can understand all of that just from looking at the data sheet and your knowledge of your system. Okay, so that's the first cross check we should do before we even lift a spanner or perhaps even put our boots on. We can maybe do that from the desktop. It's a really, really smart thing to do, and it's overlooked every single day 1,000 times. But make sure, it's a terrible analogy. Again, I'm really good at terrible analogies, by the way, is you go and buy a car or hire a car or lease a car, okay, which is meant for commuting and a little bit of business use, and you take it rallying. Guess what's going to happen? You're going to trash it because you're not using it in the way it was intended to be used. And you know that because that car would have come with certain specifications written in logbooks about what you should and shouldn't do with it, really, what it's there for and what it's not there for. Okay, so it's a very similar thing. Okay, you need to make sure that you're still using it. And I will just say one final thing before I move away from the data sheet. This also applies critically as well if you just bought a pump or you're in the process of buying a pump. These data sheets should come along with the quote, and then you can do your cross-check there before you even commit to perhaps something that's going to suffer. Okay? So make sure the data sheet, probably the most single important thing that you have that isn't actually made of metal or rubber that belongs to the pump is this original data sheet. So assuming we've checked that and everything looks kind of okay, we move on to the pump itself and how we use the gauges. Okay, so we use gauges to basically to check or confirm the system conditions around the pump as they should be. Remember, should be is just what we've just been talking about, what they should be. Okay, and we use the pump data sheet as that guide we've talked about, and if there's a difference, then that may be your problem, or at least it might be a clue to what your problem might be. But before we even talk about how we're going to use the gauges, where do we fit them? Well, hopefully, and I'm being terribly optimistic here, they're already there. but 99% of the time they're not. Okay, back in the good old days when I didn't have grey hair, pumps and systems were built and constructed, and we would put gauges on. Okay, they were a relatively small cost compared to the rest of the build cost, but they were going to give the end user, not only the end user, the commissioning engineer, and anybody that was inspecting it or looking at it during the handover phase or before that, and then obviously the end user who were operating the pump going forward. Everybody is assisted. Everybody's life is that a little bit easier because of these two little gauges. Unfortunately, they don't. They tend to get missed out these days for reasons I don't really understand, because I'm not in that game. Okay, I just tend to be involved once the things are there or when they're needed, but not actually installing them so much. But they should be there, and when they're fitted, they should be on the pump side. So the green dots, no surprise, indicate where I would put my gauge, on the pump side of isolation valves. So again, another installation tip. Really, and again, I see this a lot where it is not the case, your isolation valve should be relatively close to the pump. Why? Well, if you want to take that pump out for maintenance, okay, you're only isolating these short areas here, and you're not having to wander off somewhere else down the plant, shut something else, which might actually also be isolating another part of the system. So you want them relatively close, and that'll also be apparent why on the way we're testing it in a moment. And you want your gauges inboard, okay? Because what we're going to be doing in a minute is we're going to be manipulating these valves, okay, in order to give the pump a false head or false suction condition, and the gauges will tell us how healthy or how not healthy that pump is. Okay, it will be a measure of strength. So yeah, typical installation, that's assuming a flooded suction, but it doesn't have to be a flooded suction. If it's a PD pump and you are doing a suction lift, so you're pulling from beneath the pump or any other direction, the same kind of rules apply. All right. So if we're going to do a discharge test in this case, perhaps I should have left the green dot off on the suction side, but if we're going to do a discharge test in this case, what we're going to be wanting to do is obviously focus on the pump discharge end here. So this is our discharge gauge. This will normally be, almost always be, if it's applied correctly, a positive pressure gauge. So 0 to whatever. Let's say in this case it's 0 to 10 bar or something. Okay. And what we're going to do, so we give a step-by-step here. So we want to fit the gauges if they're not already fitted. Oh, and by the way, I should make sure I add that the gauges are, not so old that they're no longer working, or or inaccurate or whatever. But at least be confident that they're giving you an accurate reading. Okay. For this particular test, it doesn't have to be very, very accurate, but it needs to be, showing you the right numbers. Pump needs to be running. Okay. And what we're going to do is we're going to slowly close the isolation valve. Now, it might take one of you, if the same person manipulating this valve can see the gauge, but sometimes you might want your mate to assist you if you can't do that. Okay, you might, if the gauge or the valve, or they're a little bit further apart, or they're around a bend, or there's a wall sometimes, believe it or not, between the two. Okay, it might be useful to have somebody else looking at it. Possibly even if you're confident in the accuracy of sensors, which might kick back into SCADA, you might even be on the phone to somebody in the operations room or something like that. But either way, you need somebody with eyeballs on the pressure and somebody manipulating the valve. So we're going to slowly close that valve. Now, you can probably imagine in your mind's eye what's happening as we do that. The pump's running, and as we're slowly closing that valve, we're going to start to slowly oppose the pump. Okay, the flow, the flow coming from the pump, and that, because it's a restriction, is going to, or should, begin to increase the pressure at the discharge side of the pump, right? So it might be running quite happily at its normal dynamic pressure, which let's say is 1 bar or something like that for easy numbers. And we're going to slowly start closing it. And what we should see, if the pump is healthy, okay, almost straight away, perhaps after a couple of turns, just to get the valve starting to close, is we should start to see that pressure gauge on the front end begin to creep upwards. Okay. Now, what's happening there, of course, is we're opposing the discharge of the pump, and the pump, being a PD pump, is going to continue to try and deliver that same volume. And because it's starting to be opposed, it's going to push the pressure up. Nice and simple. And what we should see on a healthy pump, as we close that valve, almost for every turn, we should see that pressure, that needle, or if it's a digital one, that pressure going up in not specifically designated steps, but it should be going up in steps. It should be inching or creeping up as we close that valve. Now, how do we know how much pressure we would be getting if it's healthy? So that comes down to what size and pressure stage the pump is. For this simple example, I've used a single stage pump, which is a pump that can generate up to 6 bar before it would slip, even if it was a healthy pump. Okay, that would be like its maximum ability of pressure. But if we get I would say anything more or around 2/3 of its rated pressure, so in this case 4 bar, let's say I'm getting that and I've only half closed that valve, up to 4 bar already, then that's enough for me. That pump's healthy. It's pushing. It's clearly got a good contact, good sealing line, intact sealing line, and good clamp between rotor and stator, because as I oppose it, is beginning to oppose me. All right. However, the opposite, of course, would apply if I'm continuing to close that valve and the needle is just starting to hover or quiver a little bit above that standard 1 bar, that, dynamic 1 bar we already have, and it's just creeping up a little bit. And in my example, I say it pretty much reaches only 1.8 bar, and I've now got that valve almost closed. Of course, you always keep your hands on the valve because you might want to quickly whip it back open. You're not looking to deadhead the pump and leave it for ages. It's not going to do anybody any good. Okay, but you're not generating much pressure, so it's hardly too much of a risk, but you don't want to be leaving it there. It just doesn't do the pump any good anyway. But then just quickly whiz it, spin it back open. Okay, once you've got your feeling for what your feedback from the gauges are. But in this particular case, I'm suggesting that I've only got to 1.8 bar. I've almost got that valve closed. So that's telling me that that pump cannot generate very much pressure at all, even when I deadhead it. That pump is worn, no question. Okay, so now I can move to step 2, which might be to planning that maintenance intervention to fix that pump or switch to its standby or whatever I want to do. Okay, so really quite simple and can be done in situ. The only complicated bit about this really is getting gauges on there sometimes because they're often not available. Many pump engineers would actually carry a set of gauges with all the possible fittings, spare fitting nipples and reducers and things so that they can get them on. Most pumps have, you can just about see it if you look very carefully on this drawing, they'll have a tapping. The front end you can jump onto. They would normally have a tapping. Again, you can see them on this drawing on the suction side as well. It doesn't have to be up here. It can still be on the casing as long as it's this side of the valve. You can leap onto that, okay, providing you can, of course, isolate the pump for a couple of minutes to do that. Otherwise, you're going to have stuff squirting everywhere, but don't want to be doing that. But yeah, you can jump temporary gauges on if you need to. Okay, often they'll carry them around. They'll be on little sort of soft umbilical cords, and you can, with a set of variation of fittings, and you can jump them on as preparation for this test. I think it's quite straightforward. As I said, if you've ever got any questions, you can always call, or if you're really stuck, get somebody from Advantage Pumps to pop along and supervise it on site and help you go through it at least once or twice, or even do it on a test bench or do it in your training rooms. On the suction test, it's pretty much the same. Okay, but I thought it'd be very much worth pointing it out, okay, so that we go through it, because there can be a little bit confusion, because now we're dealing with what might be negative pressures, or probably will be negative pressures. Okay, so in this particular case, forget the front end now, okay, where we're looking at the suction side. So if we can't test at this side, okay, so that test would still, at the front end, would still tell us the same thing, whether that rotor and stator is worn significantly or not. But we're going to assume for whatever reason we can't do that there. Maybe there's not gauge, maybe that's foul, it doesn't matter. So you can also do it on the inlet side, on the suction side of the pump, and the same procedure applies. Okay, exactly the same. In fact, we're just looking at some slightly different numbers, because in this particular situation, as I'm showing you, if the liquid level is down here, okay, we already have a suction lift condition. So that gauge at normal, okay, might be showing negative 0.02 of a bar or something like that. So 2 meters pull, let's say. So that would be normal. Now, what will happen if we start to close the valve on the inlet side as the pump is running? We're now restricting, okay, what the pump can get into itself. And so effectively, and I'm going to use some layman terms here, the pump's going to try and suck harder and harder and harder to get what it wants because it's not getting it, okay? So it will almost try and turn itself inside out, not literally, don't worry. And the indication on the gauge there will be more negative pressure. So it might move from minus 0.2 bar to minus 0.3, minus 0.4, minus 0.5, okay, right up to potentially 8, depending on the size of the pump, because they can pull up to 8 meters quite healthily, most progressive cavity pumps, as a standard. So the same applies. If we start closing that valve and we get it almost closed and it's still whimperingly quivering around the 2 meters, the minus 0.2, okay, therefore that the rotor and stator is not intact well enough, not healthy enough to create the kind of suction that you want in order to lift the liquid in properly, okay? So that would also be an equivalent indication that the pump is worn out. So now we've just done 2. On the front end is one option, on the back end is another option. Okay, just simply using a gauge, running the pump, slowly closing the valve to tell us whether or not that pump is healthy. We don't have to strip it down at all. If we find it's pulling hard, one or the other, or you might want to be elaborate and check both ends anyway, just to be doubly sure, then we know that it's not the pumping element, the rotor and stator of that pump, that is the issue. What else could it be? It could be a blockage, it could be a partial blockage, it could be starvation on the inlet, it could be holes. And I've had situations where they're a suction lift like this, and there's been some corrosion to the pump where it's out of the liquid and it's starting to perforate slightly, so the pump's sucking in air, okay, rather than the liquid which it should be lifting. So it will look like the pump isn't pumping anything because it's not getting any liquid, okay, but the pump might be perfectly healthy, the pipework isn't. Okay, and other things I'm not going to go into too deep. There's some more in-depth consultations we can do. The pipe work on a new application might be too wide. It might be too large on the inlet side, and so we've not got sufficient fluid velocity to get it into the pump and get the pump primed in a way sometimes, because it's just jug really slow. Okay, so there's lots of other things like velocities and stuff which we won't need to go into, but effectively, if the pump's healthy, the pump's healthy. Look for something else. We're not going to go too deep into this because these weren't intended for today's training, but you'll get a copy of this. You can read through it in your own time. Then the slides then go on to remind you about why would the pump have been worn by abrasion usually, okay, what causes it, and then we talk about some examples about what that would look like. That's there for you, okay. Then we talk about, I need to update this slide at sometimes, although it's fine as it is, but the water industry mechanical and electrical specifications do give guidance to shaft speed. Remember I mentioned that earlier on about don't run it too fast in abrasive conditions. Okay, it gives you that guidance, gives you that top end speed. So this is 250 on what we call general sludges. Okay, our pump that we looked at a few slides ago would have been a little bit too fast if you remember what the speed was on that one. So it should be limited down to about 175 if it's starting to get quite thick. So it's going to be, concentration of grit and solids. And if you're doing heavy duty stuff like dewatered sludge cake over there, greater than 12%, then you want to be right down to 100 RPM. That has been updated recently. I do have that, but it doesn't really make any difference to the teachings in this session because the speeds are the same. Wimes have just, I was involved in it. Wimes has just added, okay, some additional possible applications like thermohydrolysis pumping and stuff like that, just to expand it. But it's pretty much the same. Most common reasons, you can read through them. Most common reasons are, we got time actually, so I'll quickly go through them. Accelerated wear, I think we touched on that enough. So the pump's either running too fast for the abrasion content of the liquid, okay, or could be foreign object damage, knives, bolts, spoons, scaffolding clips, lumps of wood. I've pulled them all out of pumps over the years. Okay, they shouldn't be there and they will damage the pump. Chemical incompatibility, that's a big one, especially if it's only dosed. Okay, often we don't think about that. Oh, it's only pumping sludge. Oh, yeah, but you're dosing ferric chloride, aren't you, or ferric sulfate? Oh, yeah, forgot about that. Well, that's going to have a detrimental effect on the metallic elements of that pump. Some of the rubber bits too. Cavitation, okay, a lot of us know about cavitation. It's slightly different in a PC pump. It's a lot more violent. It doesn't just sit there, get hot and fizz. It will actually replicate what I talked about earlier on, where you're starving the pump on the inlet. The pump will start to react really, really violently. And I would switch it off on the e-stop as soon as you can before something breaks. Overpressure, okay, that's the opposite end case. So if there's a rolling blockage or somebody shut a valve or a valve's accidentally shut when it shouldn't do. Dry running, when you're getting no liquid in at all, okay, so the rotor and stator are just spinning together, or the rotor spinning within the stator. There's no liquid going through it to keep it cool. It relies on that to an extent because the frictional heat that it would make for itself anyway, and it will start to break down the rubber of the stator. The rubber material in the stator will get way too hot and it'll either melt or it will harden off or glaze, as some people call it. If that ever happens, by the way, and you take a pump apart and you're not sure if that's what's happened, you will know because you just smell that stator, and even over any overpowering, should I say, existing odor, that if the stuff you might have been pumping, it will still smell like burnt tires. It'll be very obvious. Temperature damage, if the sludge or the media or the liquid is far hotter than the pump was originally intended for, you can get failures on the joints because the grease can't handle that level of temperature, and also you get a lot of thermal expansion. So the clamp will go up rather than come down like it does with wear. Okay, so your rotor will expand, parts of your stator will expand with the heat, they will grow, and they will be too tight, and you'll often find that the pump won't even start. Most common of all, operating off the data sheet. We talked about that, right? Most problems are man-made. Faults and failures. This talked about. This is just a guide if you're walking into a pump space and you've only got touch, smell, and sound. Okay, you can tell. These are kind of more expert, a lot of experience things, but you can learn them. It's probably best if you hear them yourself once or twice so you remember them. But cavitation, heavy banging, it will literally sound like somebody's hammering the thing with a hammer. Okay, rotor stator, get your ear close to the rotor and stator. You'll hear like a swishing sound, like a washing machine emptying. You're hearing the slip. Okay, it does make a noise. Most things do. Overpressure, like I said, it's similar to the first one, but then the banging is slightly different. It's more of a thumping than a banging. Failure of use of universal joint, you'll get a clicking. That's before it's failed, by the way, not once it's already failed. You'll get a clicking emitting from the pump, and it'll be rhythmic with the same speed of the shaft. Valve mechanical seal, usually quite obvious. You've got leakage on the floor, right? But not always. If the pump is doing a suction lift in particular, then stuff's going to take the least path of resistance. So the air is going to rush in where the seal is, okay, rather than the liquid coming up through the pipe. And you can hear that. You'll hear the air rushing or being sucked in, okay, at the point of the mechanical seal. Again, really common. All right, the seal goes, but you can see no leakage because the pump's actually generating a slight suction to get it. So you won't get visible leakage. There's negative pressure where the seal is. So what you will get is you will get no flow because the air's getting in there and the pump's trying to just pump air bubbles, really. Okay, but you will get a sound. Chip teeth on the gearbox, fast clicking sound. That's nice and easy. Put the screwdriver to here and put it on the casing. Failed bearings. Okay, lots of ways you can just spot that, but usually it's a squealing, grinding sound. This is just a few reasons as to why things would have happened. I'm not going to go through all of them, okay? But if you look at the bottom three, pump run down on flow, error on the flow meter, big one, happens a lot as well. We blame the pump, we take it apart, we buy 10 grand's worth of spares, but all along the flow meter it was giving us some lies. Down on flow, sheared shafts or joint, yes, the pump can still run. The motor might be running and the gearbox will be turning, but the rotor actually isn't because one of those transmission joints is broken, sheared off. Or just the wear, okay, but the top ones I've already covered. Preventative measures, check the performance regularly, okay. You could, and many people as part of PPM will do a closed valve test, okay, the smart ones, no offense, but they will, once every 6 months or 3 months, they'll go and they do a quick closed valve test and say, yep, that pump's healthy. Oil changes, of course, yeah, in the gearbox, they are all filled or half filled. Service areas of those joints, if required. Some brands require you every 40,000 operating hours to strip those joints. It's not very practical, but they do, and the warranties will be void if you do not. Check running speeds. Are they appropriate? Remember, we'll go back to the data sheet. If you've started to have more demand or for whatever reason you need to increase the flow and you sped the pump up, was it an okay thing to do? Yeah, it might have got you more flow, but is it now going to have a detriment to the pump's wear in the short term? Okay, yeah, most important is to make sure the pump is appropriate for the duty, which we've covered in the data sheet, okay? The speed is appropriate to abrasion, the pressure stage is appropriate to the pressures you expect, the temperature is appropriate to the temperatures you should expect, and the material selection is appropriate for the liquid you're pumping. You can have protection. Dry run protection will sense frictional heat and it will trip the pump out. Over pressure and under pressure, they're self-explanatory really, but they're pressure switches which will should be linked back to the panel and trip the pump before any major damage occurs.